Hey everyone, welcome back. In this video, we will try to understand about prospect theory, which is the base for KTO optimization. Prospect theory concept is taken from human psychology. Prospect theory is made up of three different components: human aversion, diminishing sensitivity, and probability weighting. What is loss aversion? Humans experience losses more intensely than gains of same size. What do you mean by this? So now let's consider two scenarios. In scenario one, a person is walking on the street and he suddenly found $100. In scenario two, the same person lost $100 from his wallet. So the kind of experience that this person faced when he lost $100 is much more intense than when he gained $100. Right? Though the value is same, but the kind of experience is very, very intense for losses than gains. This is what is loss aversion. So, what is diminishing sensitivity? It says that humans are more sensitive to small changes near reference point. So, now let's assume in a given month, we are expecting a salary of 100K. As we are expecting, let's assume our reference point is 100K. So, in that month, let's assume you got 120K as your salary, 20K profit, right? So, now you feel very happy. In the next month, now you got 140K in the next month, right? You will still feel happy, but the amount of happiness is not twice as good as when you got 120K, right? Why? The reason being is because of diminishing sensitivity. Because 100K is a reference point, right? We are very, very sensitive near the reference point. As we move away from the reference point, right, that sensitivity changes, right? Even when you got 140K, you will still feel happy, but it is not twice as good as when you got 120K, right? Because you moved away from the reference point. So the next one is probability weighting. It says that 1% feels more than 1%, 99% feels less than 99%. So what do you mean by this? Let's assume people still buy a lot of lottery tickets, even when they know the chance of winning is very, very less, right? Even when the chance of winning is still very less, they'll feel that probability of them winning the lottery is high, right? Here, 1% is feeling more than 1%. Let's take one more example. People fear flying more than car driving. Even everyone knows that flight crashes are very rare, right? Even when flight crashes are very rare, people will feel that flight might crash. So here, 1% probability of a flight crashing is feeling more than what it actually is, right? So car crashes are very often, right? Let's assume it is 99%. Just for assumption, let's assume it's 99%. But still, people feels that driving in car is very safe, right? Here they are thinking that 99% is less than 99%. So now we don't use probability weighting for our KTO optimization. There are lots of reasons for that. We'll see that reasons in the end of this video. So now this is how we mathematically represent prospect theory without probability weighting, right? So this consists only of diminishing sensitivity and loss aversion. Even in the research paper that you see over here, you can see the same equation without probability weighting. Let's try to understand this equation. So now let's consider only loss aversion, right? So this is how the equation looks if you remove diminishing sensitivity. How to read this equation? When you say V is nothing but you can think of it like a value of experience, value of human experience, right? If value of human experience is positive, then V value will be positive. If the experience is negative, then the V value will be negative, right? So now we'll see what is Z and what is Z naught, right? So now let's assume in a given month, we are expecting a salary of 100K. So Z naught equal to 100K. In case one, assume that the salary that is credited is 120K. So then Z will be equal to 120K, right? Because Z is greater than Z naught, right? V is equal to Z minus Z naught, right? Because as Z is greater than Z naught, V is equal to Z minus Z naught. And Z minus Z naught is nothing but 20K. So now the value of human experience when he gained 20K is 20K. So in the next case, human is anticipating 100K, right? But the salary that is credited is 80K. Now Z is 80K because Z is less than Z naught. V is minus lambda of Z naught minus Z, right? So here in this case, I got a loss of 20K, right? So now then V value is minus lambda into 20K. If I assume lambda equal to 2.25, then V value will become minus 45K. That means the value of human experience is minus 45,000. So in the first case, we got a profit of 20,000. In the second case, we got a loss of 20,000. But if you just compare the values, right? Value of human experience in first case is 20,000. Value of human experience in second case is minus 45,000. So loss of same amount is 2.25 times more painful than gain of same amount. How are we achieving this? We are achieving this by using something called as lambda. Because of negative lambda, right? Uh, you are creating that additional intense experience, intense negative experience in this case. So now I hope this is clear, right? So this is how we derive V when we consider only loss aversion. So now let's consider diminishing sensitivity. What is diminishing sensitivity? It is nothing but humans are more sensitive around the reference point. So now let's assume we are anticipating zero profit. Right? We are anticipating zero profit. So somehow we got a profit of $100. So here, if we assume alpha as 0.88, 100 power alpha is 57. So in next case, let's assume the profit that we got is 200. Right? So 200 power alpha, that is 200 power 0.88 is 0, I mean, it is a 104. So now, though the profit is double over here, the value of human experience is not double, right? I mean to say the value of human experience when we got 200 profit is not 57 into 2. It is slightly less than that. Right? That's what diminishing sensitivity says, right? We are achieving diminishing sensitivity with the help of alpha, right? So now let's consider loss as well. We are expecting zero loss. So somehow we got $100 loss. Let's assume this, right? So now we have lambda equal to 2.24. So the value of human experience when we got $100 loss is represented as minus lambda into 100 power alpha. It is minus 128.9. In next case, let's assume we got a loss of minus $200. In that case, the value of human experience is minus 237. It is still bad, but it is not as, I mean to say, it is not twice bad as when we got $100 loss because we are moving away from our reference point. So now if you combine both these cases, if you combine alpha, right, which talks about diminishing sensitivity, and if we combine these two cases of loss aversion, this is how our mathematical representation of prospect theory looks like. If we consider both loss aversion and diminishing sensitivity, right? So here alpha represents diminishing sensitivity. The rest of the components represent loss aversion. So now let's come to next part, probability weighting, right? I've mentioned at the top, like probability weighting is not a part of KTO optimization research paper. For a moment, let's assume what if we include probability weighting in our prospect theory or in our prospect theory mathematical representation, right? So what is probability weighting? 1% feels more than 1%. 99% feels less than 99%. How do you mathematically represent it? We represent it using this equation, right? So now for gamma equal to 0.61 for a probability of 1%. If you plug in both these values in this equation, for a probability of 1%, this probability weighting value will be 5%. 1% is feeling more than 1%. So now for a probability of 90%, if you plug in the values of gamma and 90%, so the output of this function will be 71%. So high percentage is feeling less than that percentage, right? So if we add this, if we add probability weighting to our prospect theory formulation, this is how it looks like. Right? We have just added this probability weighting over here. So now, what are the disadvantages of this, right? So this probability weighting, this function is very, very nonlinear, right? We are adding a very, very high amount of nonlinearity, and because of this, the computation of gradient is very, very complex, right? So if you wanted to solve any optimization problem, most of the optimization problems in machine learning will be using something called as gradient descent. If we have probability weighting as a part of our loss function, right, calculating this gradient is very tough. And sometimes what happens is for such kind of complex functions, there will be very high chance of gradient explosion and gradient vanishing problems. Also, in scenarios like games and lotteries, we know what is the probability of rare event. If we think like certain event is rare event, we can inflate the probability of rare event, right? Because that's what is probability weighting. One person feels more than one person. If we think like certain event is very, very highly probable, we can slightly reduce that probability value, which is 90% feels less than 90%, right? But in case of text generation, it is very hard to define what is rare event and what is very frequent event, right? It's very hard to define. So because of, sorry, all these reasons, researchers did not consider probability weighting as a part of prospect theory formulation. So this is what you can see in the prospect theory section of the research paper. I think pretty much that's it for this video. See you in the next video.